So in 7.3, we're going to show how an integral and formulas from geometry are related to each other. So we talked briefly about regular shapes. These are the shapes that have formulas for area. And so we talked about some common ones. Your rectangular solids. This could be a square or a rectangle. And pretend like that's a rectangle there. So if this is the length and this is the width, the area is the length times width. We talked about triangles. And so when you have a triangle, you have a base and a height, and the area of that is 1/2 base times height. There are other shapes. There's all kinds of parallelograms. The area of this is base times height. Base and height. Then you have circles. And the area of a circle is pi r squared. And there are other shapes. There's a trapezoid and a rhombus and other things. But these are what we consider regular shapes, and they have formulas for area. And what we're going to do with the integral is we're going to eventually have an irregular shape. So say, for example, we have maybe part of a fourth power function. So, and we want to know the area inside of here, okay, between the curve and the x-axis. Now, the x-axis is a horizontal line. Okay, that's our x-axis. And so it has an equation, y equals 0. So because the bottom border of our shape is y equals 0, we won't have to deal with anything except for this actual curve itself. Now, if we wanted to find the area between two curves, which we'll talk about later, let's say we want just this area in here, then we would need to know the equation of this curve and that line or curve or whatever it is. So when we want to find that area, we're going to use what's called the fundamental theorem of calculus. And it says, looking at a function, f of x dx, from points A to B, then where f is the original function, now the way they write that is f of x, where f is the antiderivative. It's the original function, okay? This derivative has been taken, and this big F means original function. Okay, so we've taken the antiderivative and gone back. And so they write this original function, capital F of x, b, a. And so all you do is you evaluate the function at b, and then you subtract from that the function evaluated at a. And you're going to see this working as we do some of these problems. Okay, so let's look at this first one again. What we're trying to do is we're trying to find the area in here, okay? And so you'll see how they've set it up. They've set it up as from 0 to 10. All right, because here's 10 right here. So from 0 to 10, f of x dx is going to be that area in that space between that curve, which happens to be a V shape, and the x-axis. We're going to relate it to the geometry, and then later on we'll talk about how can we find that actual value using the calculus. So all we have to do is 1/2 base times height. 1/2 base times height, because this is a triangle, right? So 1/2 times 10, and the height of this thing right here is 1, 2, 3, 4, 5. So half of 50 is 25. Because that's what the integral tells us, that it's going to give us that area under the curve. Now for part B, we're finding the area in here and the area in here. And so this goes to 10, okay? And it's going to be two triangles. So it's going to be a 1/2, a base times a height, plus that little one, 1/2 base times a height. So this first base goes to 9. So it's 1/2, 9, and then this is 1, 2, 3, 4, 5, 6, 7, 8, also 9, plus 1/2. This base is 1, and its little height here is also 1. So that's half of 81 plus half of 1. That's 81. So that's 81 over 2 plus 1 over 2 is 82 over 2, or 41 units. So that area is going to be 41. Now, again, we're going to use this when we actually have the function. So notice here they just gave us a picture. But when we actually have the function, we're going to use this fundamental theorem of calculus to let us do the same thing. Now, number 2 is a circle, and you may not recognize that, but x squared plus y squared equals 16 is a circle at 0, 0. That's the center, and a radius of 4. Okay, so if we solve that for y, that's going to be 16 minus x squared. So y would be the plus and minus square root of 16 minus x squared, but they only ask us to look at the positive one. So we're looking at y equals the square root of 16 minus x squared. So what that means is, instead of the whole circle, going from 4 and -4 and 4 and -4, they only want us to look between 0 and -4, and they only want us to look at the positive part. Okay, so this is what they're asking us for right here. Just that little piece. Okay, this would be the negative part. So we said earlier the area of a circle is pi r squared, but this is 1/4 of the circle. So the area we want is 1/4 pi radius squared. And our radius is 4. So we want 1/4 pi times 16. So that's 16 over 4 pi, which is 4 pi. Now you might have something like the square root of 25 minus x squared. Well, that tells you that you're looking for that quadrant, and depending on, let's say they give us from -5 to 0. So you're looking for that quadrant where there's a radius of 5. So you do it similarly the same way. The square root of this number right here, that's going to tell you what your radius is that goes in your R value of your formula. So in number 3, they ask us to find the exact value of the integral using formulas from geometry. And this time they actually give us the function and not the picture. So what they're saying is that f of x is 2 plus x. So we're going to make us a little chart. And they tell us they want us to find it from 3 to 5. So I'm going to go ahead and let the x's be 3, 4, and 5. And then 2 plus 3 gives me a 5 here. And this is going to be 2 plus 4, which is a 6. And then 2 plus 5 is a 7. So those are 3 points, and this is just a line. So let's draw our line. So I'll go over 3 and up 5, over 4 and up 6, and over 5 and up 7, and I'll draw the line through that. So that's approximately what it looks like. Okay. Now, what we're asked to do when they give us this integral is find the area between that line, which is, we can call it a curve, but you know it's not really curvy, and the x-axis down here. So the area I'm actually looking for is this area here, just between 3 and 5. Well, that shape is a trapezoid. So let's review what a trapezoid is. A trapezoid is a shape that has 2 parallel sides and 2 sides that are not parallel. So something like that. And in a trapezoid, we have an upper base and a lower base, or a small base and a big base, and then we have a height. And so that's the part that we need, the parts that we need for our formula, which is 1/2 height, base 1 plus base 2. So in our case, from 3 to 5, that's technically our height. That's a 2. So it's 1/2 times 2. And then the length here is our top base, and here is our bottom base. Well, at 3, that goes to 5. So this length here is 5. Okay, and this length here is 7. So it's 1/2 height, which is 2, 5 plus 7. So that's 1/2 times 2 times 12. And then 1/2 of 2 is just 1, and 1 times 12 is 12. So the area of that shape is 12. So this integral has a value of 12. Now this is called a definite integral because we know the endpoints, okay? This is what makes it a definite integral. We know we're starting at 3 and ending at 5, so we know what we call the boundary values. So this lower bound is 3 and the upper one is 5. Now let's do it by the calculus. You'll see it's actually easier. So from 3 to 5, 2 plus x dx is, well, the integral of 2 is 2x. Integral of x is x to the second divided by 2. And since we have a definite integral, we don't write the plus c, but we write a vertical line 5 and 3, which means we need to evaluate it at 5, evaluate it at 3, and subtract. Remember, that's the fundamental theorem of calculus. All right? So we have to find f of x we found to be 2x plus x squared over 2. So we need to find f of 5. That's 2 times 5 plus 5 squared over 2. 10 plus 12.5 is 22.5. F of 3 is 2 times 3 plus 3 squared over 2. That's 6 plus 9 over 2. 6 plus 4.5 is 10.5. So this is going to be 22.5 minus 10.5, and that turns out to also be 12. So look, we got the same answer as we did when we did it by a geometry formula, because that's what the fundamental theorem of calculus does. It finds the area between a curve and the x-axis given the two endpoints where you have to start and end. All right. The total revenue for a product can be calculated as the area under the demand curve. Okay? So, in other words, if you have a demand for a product, and that's what the curve looks like, and you want to know the total, so you're looking for area between the curve and the axis, okay? Now, they want us to approximate the revenue first by using what they call the left endpoints and then by using the right endpoints. Now, it would absolutely be easier just to do the calculus on this, which would be from 0 to 50, right? They tell us 0 to 50 of 1/10 q squared minus 10q plus 265 dq. That will give us the exact. Okay. And first they want us to estimate it. So let me show you what they mean by this. And what we're trying to find is this. All the way up to 50. Okay. Now we could do that by integration, but what they told us to do instead is to do it by drawing rectangles and with widths of 10. So we've got to go to 50 divided by 10. That means we're going to have 5 rectangles. So let's see, here's 10, 20, 30, 40, and here's 50. Now we're doing rectangles, so we've got to go here's my, let's see. Here's my first rectangle right here. Okay, because they want me to use left rectangle, so this first height is going to be right there, okay? My second height is going to go from the left to right here. My third rectangle is going to go from here to here. My fourth rectangle is going to go from here to here. And my fifth rectangle is going to be that little rectangle right there. Now you'll notice in every one of these we've got excess. Let's see. Okay, that's extra stuff. Okay, so we're just getting an estimate. This is going to be an over estimate. Okay, now every one of these rectangles has a width of 10. All right, and remember we're just doing length times width. Okay, and the height, or the if the width is 10, then this length is this taller part right here. And that's the function value there, 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 and there. So we're going to make a table using x is 0, 10, 20, 30, and 40. Now, when we go from the left, we're not going to use 50 because our last rectangle starts at 40. So if I put a 0 in there, I'm going to get 265. So that first height is 265. So length times width, okay, is 265 times 10, which is 2650. Now when I put 10 in there, I get 1/10 times 10 squared minus 10 times 10 plus 265. That's 1/10 of 100. You can do this on your calculator for sure. Plus 265. So that's 10 minus 100 plus 265. So that's going to be 165. It's going to be 175 times 10 is 1750. And absolutely use your calculator on this, okay? And you can use 0.1 instead of 1/10, or you can use your fraction key. Here I have 1/10 times 20 squared minus 10 times 20 plus 265. That's going to be 1/10 of 400 minus 200 plus 265. So what is that? That's 40 minus 200 plus 265. That's 105 times 10, 1050. This is the length of the rectangle right here, okay? We know the width of all of them is 10. So look, these are in 10 increments. That's going to be 1/10 times 900 minus 300 plus 265. That's going to be 90 minus 300 plus 265. That's 355 minus 300, so that's 55 times 10 is 550. Now, notice that these are going down because, look, this bigger rectangle has the most area, and then these are getting smaller and smaller and smaller, right? Because the heights are shorter and shorter and shorter. So the last one is 1/10 times 40 squared minus 10 times 40 plus 265. That's 1/10 of 1600 because 40 times 40 is 1600 minus 400 plus 265. That's going to be 160 minus 400 plus 265. Let's see, 265 and 160 is 425 minus 1. So that's going to be 25 times 10, 250. So the total area estimated is 2650 plus 1750 plus 1050 plus 550 plus 250. And so when I add all that up, I get 6250. And that's the area of the total thing if I find the area of every one of those rectangles. And it's an overestimate. So 6250 here. Now I have to go back and use the right edges. Okay, so let me erase this. And we're still doing widths of 10. So 10, 20, 30, 40, 50. But we're using the right endpoint. So this time, we're going to go there, 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 and there. So look, this time, we're going to be an underestimate. The last one was an overestimate. This one is an underestimate. Because look, we're missing this area, this area, this area, this area, and this little area. Because we're just doing base times height, or length times width. Look, our width is 10, and our height is whatever this distance is up to this right endpoint. And our width is 10, and our height is just to whatever that distance is right there. Okay? And then the same thing here, and the same thing here, and the same thing here. So we've got to evaluate the function starting at 10 instead of at 0. All right? Now, we already know 10, 20, 30, and 40. So let's just copy this. Now I want to include 50. Okay? So it's going to be 1/10 times 50 squared minus 10 times 50 plus 265. So that's going to be 1/10 of 2,500 minus 500 plus 265. So that's 1/10 of that is going to be 250 minus 500 plus 265. And let's see, 250 and 265 is 515 minus 500. So this is just 15 times the width of 10 is 150. So this time the area here here, 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 and here is 1750 plus 1050 plus 550 plus 250 plus 150. So if I add all that together, I get 3750. Now remember, this is an underestimate. 3750. That's with the right endpoints. Okay. Now the average of these two, 6250 plus 3750 divided by 2 is 10,000 divided by 2 is 5,000. So that's the approximate revenue using rectangles. $5,000. Let's go ahead and do the calculus and find out what the actual revenue is. So they want us to go from 0 to 50. And you're going to see that the calculus is easier. Okay? But basically the calculus is doing this. The only difference about what the calculus is doing is instead of these wide rectangles, it's making the width of the rectangle be smaller and smaller and smaller. So literally you're adding every one of these points up. You got a lot of teeny tiny little rectangles, adding them up. And the smaller the rectangle, the more accurate your estimate's going to be. Okay? So let's go ahead and just do that. This is called a definite interval because we have the endpoint, so we don't need a plus c. All right, so we'll take our integral just using power rule. So that's going to be 1/10 times q to the 3 over 3 minus 10 q squared over 2 plus 265 q, okay? And that's going to be evaluated at 0 and 50, okay? And we do the 50 first and then the 0 last. So that's going to be q to the 3rd over 30 minus 5q squared plus 265q. And so that's our f of q. So we need to do f of 50 and f of 0, and then we'll subtract those two values. So f of 50 cubed over 30 minus 5 times 50 squared plus 265 times 50. So I'm just going to do that on the calculator. 50 to the 3rd divided by 30 minus 5 times 50 squared plus 265 times 50. I'm entering it just like you see it there. And that's 4916.67. Okay? And f of 0 is, look, it's going to be 0 cubed over 30 minus 5 times 0 squared. 265 times 0, so 0. So it's 4916.67 minus 0 is 4916.67. That's the exact amount versus, remember what we got? We got 5,000. Okay? This is an approximate revenue, and this is the revenue from 0 to 50.